Alright folks, for our final video of this rotation unit, we're going to talk about angular momentum. We are going to start with Newton's second law for rotation and do essentially the same thing that we did with Newton's second law when we talked about impulse momentum. And so we will just do that. So we're going to use two equations here. We're going to say that torque is equal to R times F. So we'll imagine a single force is causing a torque. And the definition of angular acceleration, which is change in angular velocity over time. And so we'll imagine that the net torque is due to a single force that's causing a single torque. And so what you end up with when you combine everything is R times F, and that equals I delta omega over delta t. And so if I rearrange this, I have Rf times time equals I times change in angular velocity. And I don't know why I did that right there, but so we're just going to go back to kind of the original and say torque times time equals I times change in angular velocity, because this is really how it's given. So torque times time is called angular impulse. So if there is a torque that is delivered for any amount of time, it delivers an impulse, and that impulse is going to be used to change the rotation of an object. I times delta omega is change in angular momentum. So the impulse-momentum relationship works for rotation. If we switch out force for torque and velocity for angular velocity, and then mass for moment of inertia. And so the things that come out of that is this equation. So L equals I omega. And so this is the definition of angular momentum. And you'll see that it's very similar to linear momentum. P equals mv, where m is now I and v is now omega. So the analogs are all in the same place for basically all of these equations. The units for angular momentum are kilogram meter squared per second squared. Not per second, no, sorry. Kilogram meter squared per second. So they are, again, like similar to the units of linear momentum, but they have that extra meter in there. Okay, so objects can have angular momentum as long as they are rotating at all, and that's nice. Same thing with momentum. The more inertia, the more momentum that object can kind of pack in, and so objects with a lot of rotational inertia can have a lot of angular momentum. So we'll explore some of like the classic demonstrations of angular momentum in here, but basically the last thing I wanted to do was say, well, this is for an extended object. So if I'm, like, again, rotating the meter stick, then it has an angular momentum as long as it has any angular velocity. But the question becomes, like, what if instead of rotating a particle, an extended object, you are rotating an individual particle? And so what you're going to see here is how angular momentum gets us back to linear momentum. So we're going to start with the definition. Well, that's not working out well. The definition of angular momentum. So moment of inertia times angular velocity. And if it's a single particle, then the moment of inertia equals mr squared. And the linear velocity equals r omega. So I'm going to make like a double substitution here. We're going to say, and by now you're like, yeah, whatever, I'm used to it. So moment of inertia is mr squared. Angular velocity, if I solve this for omega, I get v over r. And so I've got some canceling to do and then some simplification. This becomes mr times v. And so something fairly interesting happens. Momentum, linear momentum, is m times v. So if I take that out of this equation, for a single particle, I get that the angular momentum is the distance that particle is away from the axis of rotation times momentum. And so, there was like one problem in the linear momentum unit about someone in a baseball game, and there was a collision between the bat and the ball. Well, as it turns out, particles can also have angular momentum, and so another way to analyze the situation with the baseball is to say, even though the baseball is moving in a straight line, when it collides with the bat, it enters into a rotational system. For that instant, it's part of the system of the bat and the ball that are both rotating around the axis. That's like maybe like the batter's shoulders or wrists, depending on what he's doing with the bat. And so angular momentum can be in terms of a single particle. As long as there is some kind of excuse for rotation to be involved, you can use this definition for angular momentum. And so we will explore a lot more about that in class.